So if you remember, we said that we could use power series to create new and interesting functions in a different way. And we're going to now put that to the test even more so. Because if we have a power series, c sub k x to the k, that converges to f of x, and then we have another power series, d sub k x to the k, that converges to g of x, respectively, both on the same interval, right? Notice that it's on n interval I, so same interval. Then we can actually combine them together to make a new power series that will converge to the sum or difference, depending if we did sum or difference, on that same interval I. Moreover, we could multiply. So if we have m, which is an integer, such that k plus m is greater than or equal to 0, k being our index, for all terms of the power series, x to the m sum c sub k x to the k is equal to the sum c sub k x to the k plus m. In other words, I can add my powers of x to make a new power, which is k plus m. And that series will converge to x to the m times f of x for all x not equal to 0 in that interval. When x equals 0, the series always converges to whatever the limit was of x to the m of f of x. And then we can compose. We can take a power series where m is a positive integer, we take a function b x to the m where m is a power of an integer, and then we have a power series c sub k h of x to the k, and we can put that function inside that power series and make a new function. Fascinating, huh? So this is going to be some work. Let's start off with one that we know of, the geometric series. So we learned a few pages ago that the geometric series looks like this, so 1 plus x squared and so on, and that it's equal to 1 over 1 minus x, that's key, for x less than or equal to 1. That would be the radius of convergence. Now, we're going to use that to find a power series representation for this function, which is 1 over 1 plus x cubed. Okay, so where we're going to start is by comparing these two, because that's my function, f of x, right here. Here's f of x, and it's also all of this, right? It's both things simultaneously, and here's g of x. So I'm going to rewrite g of x. G of x is equal to 1 over 1 plus x cubed. That I want to get it into the same form as f of x. So I want a subtraction. So I'm going to go 1 over 1 minus negative x cubed. That would work, right? Because negative times a negative would be positive. But that means now take your series, because this guy right here is now your h of x. So if you look, I've composed one function and another. So h of x is equal to negative x cubed. Okay, so now let's rewrite our series. So we rewrote g of x. Now let's rewrite the series, which is equal to because they're tied together, right? So we rewrote the function. Now we're going to rewrite the series, and they're equal to each other because the functions they're built from were equal to each other. I'm going to go from k equals 0 to infinity, and it was x to the k. So when I look at this function, f of x, it was 1 over 1 minus x. That was equal to x to the k right here. So now, instead of having x to the k, I'm going to have negative x cubed to the k. Right? My h of x is being composed in my series. I'm nesting h of x into my power series, like that. Now that would be equal to, and I can break the negative off, and I can say, okay, that's k equals 0 to infinity. That would be negative 1 to the k, and then x to the 3 to the k, which would be a series from k equals 0 to infinity, negative 1 to the k, x to the 3k. All right, so I found the power series representation right here. So right there, I did it. I answered the first part because they say, find the power series representation, and I did so. The power series representation is right here. What I haven't found yet is the interval of convergence, but here's the power series, my new power series. It was built from the old one that I knew right here, but I built it into something new. So this power series represents that function, whereas this power series right here, x to the k, represents that function. Now all I need to do is find the interval of convergence. All right, so interval of convergence. Okay, well, the interval of convergence for the original was that the absolute value of x must be less than 1. But for me, I'm going to put in h of x, right? I need the absolute value of h of x to be less than 1, right? So I need the absolute value of h of x is negative x cubed, to be less than 1. All right, well, the negative is not really going to be a problem because it's inside an absolute value, so I don't really care about that. Now I want to get rid of the cubed, so I'm going to take the cube root of both sides, because why not? Right, so if I take the cube root of that side, take the cube root of that side, the negative's kind of irrelevant, so it doesn't really matter because it's inside an absolute value. And I'm left with the cube root of the absolute value of that, which would be x, and then the cube root of 1, which is 1. So there's my interval of convergence. However, I need to check my endpoints. So I need to check endpoints. I can't just circle that and say I'm done. I don't know about negative 1 and 1. So keep in mind what this means. It means negative 1 is less than x, which is less than 1, right? So I need to check and make sure negative 1 and 1 are not included. So let's let x equal negative 1. And then we go back to this lovely series and we substitute it in. So we say, okay, I'm going from k equals 0 to infinity, negative 1 to the k, and instead of x, I'm going to have a negative 1. Oop, to the 3k, not 3x. Sorry, 3k. Okay, so negative 1 to the k is negative 1 to the k, and negative 1 to the 3k. So this is going to be negative 1 to the 4k here. Right? They have the same base, different powers, so you can combine them together and just add the powers. 3k plus k makes 4k. But negative 1 to the 4 is positive, right? So this will always be positive because 4k is always an even number. So this is the series of 1 to the 4k. In other words, it's 1. Because it doesn't really matter how many you're doing, right? You're just adding them, right? So honestly, you could just say 1, right? Because it's just 1, right? No matter what k value you put in 0, it'll be 1. Put in 1, it'll be 1. Put in 2, it'll be 1, right? So put in 2, 4 times 2 is 8. Negative 1 to the 8 is 1. So honestly, you could get rid of the 4k entirely because it's not even there. It's just 1 plus 1 plus 1 plus 1. That's divergent. That doesn't pass the divergence test. Remember the divergence test, right? You have to have the limit be 0 of your nth term. And this is not. So, right, divergence test. Your limit of your value, your sequence term, has to be 0. That doesn't. So that diverges. Right, it fails divergence test. Well, I suppose it passes the divergence test in that it diverges. All right, then we try x equals 1. So that would be from k equals 0 to infinity of negative 1 to the k times 1 to the 3k. Okay, well, 1 to the 3k is just 1. I mean, the same issue I just had. It's 1, 1, 1, 1, 1, 1, all the way down. So this kind of goes away. Doesn't really matter. And I'm left with negative 1 to the k. So that diverges, right? It doesn't pass the divergence test either. So negative 1 to the k, the limit of that is not 0. It actually flip-flops. It goes 1, 1, negative 1, 1, negative 1, 1, negative 1. So it never goes anywhere. So that also fails the divergence test. And that means that our interval of convergence, now we can say it, is this, because we checked the endpoints. Or we could say this, which is the way I would prefer to write it. So my interval of convergence is -1 to 1. I checked the endpoints, and neither one of them was any good.